Picture a network of 1 million computers sharing files, with no master server and no central directory anywhere. Somehow, you can still ask who holds one particular file and get an answer. That is a distributed hash table. The whole idea starts with one shared number space, enormous, like every integer up to a huge power of 2. A single hash function maps anything you feed it to one position, an ID, somewhere inside that space. Feed it the name of a file and the hash spits out that file's key ID, a fixed point in the space, say position 7000. The name alone decides the number, nobody hands it out. Here is the move that makes the whole thing work. Every node, every participating computer, is fed through the same hash and lands its own ID in that identical space. Keys and machines now live side by side. One rule ties it together. Each key is the responsibility of the node whose ID sits closest to that key's ID. Ownership is decided by arithmetic, not by any coordinator, and it lands wherever the numbers fall. But no single node can know all million others. Instead, each keeps a compact routing table of contacts, deliberately biased so it knows IDs near itself in fine detail and distant IDs only in broad strokes. That bias is exactly what makes lookups fast. A query hops from node to node, each step landing closer to the target ID, so any key is found in roughly log and hops instead of a linear search. Finally, durability. A key is not trusted to one machine. It is copied onto several of the nearest nodes, so a single computer leaving the network never means the data quietly disappears. Let us watch one lookup unfold. Take one, you hold only a file's name and want whoever is responsible for it. Your node feeds that name into the shared hash function, the first move in every DHT lookup. Out comes the key ID, a single fixed point in the number space. This is the address we are hunting for, and notice it was computed, never looked up in any table. Meanwhile, every node already carries its own ID from the same hash. So the key ID and all the node IDs sit together on one imaginary ruler, ready to be compared by simple distance. Now the core rule fires. Compare the key ID against every node ID and pick the one that is numerically closest. That node and only that node is declared the owner of the key. No vote, no coordinator. But there is a catch. Your node has no global list, so it cannot simply see who is closest. It must search. It starts by asking the best contact it already knows toward that target. That contact comes from the routing table. Because the table knows nearby IDs finely and far IDs coarsely, even a first guess at a distant target still points meaningfully in the right direction. Each node you reach hands you back an even closer contact, so every hop shrinks the remaining distance to the target ID. You are always moving nearer, never wandering sideways or backward. Because each hop can roughly have the distance that remains, the number of steps grows only with the logarithm of the network. 1 million nodes are reached in about 20 hops, not 1 million. Within those few hops, the search arrives at the node whose ID is closest to the key. The lookup is done. This is the responsible node, and it holds or can fetch the value you asked for. To survive failure, the owner is never alone. The same key is replicated on several of the next closest nodes, so if the responsible node drops offline, a neighbor already holds an identical copy ready to serve. Now the honest hard part. Nodes join and vanish every second, so the closest ID owner for a key keeps changing. This constant turnover has a name, churn, and it never stops. So responsibility boundaries drift as neighbors appear and leave, and every routing table must be repaired continuously in the background. A DHT is less a fixed structure than one that is always healing itself. Step back and the payoff is clear. No central directory exists, yet every key still has a definite, findable home. Structure and responsibility emerge from arithmetic alone, spread across thousands of equal peers. That openness invites abuse. A hostile node can deliberately choose an ID that sits right beside a target key, making itself the rightful owner and capturing every request for that particular value. The defense is to make IDs unforgeable. Derive each node ID from its public key, so an ID cannot be freely chosen. now sitting exactly next to a chosen key becomes computationally impractical. A subtler attack is Eclipse. Flood a victim's routing table with malicious contacts until nearly every entry points at the attacker. The victim then sees only a fake slice of the network. Despite all this, DHTs run real systems: file sharing indexes, content address storage, and peer discovery. The trade against a central index is plain: no single point of failure or control, paid for with lookup latency and complexity. The full picture: hash keys and nodes into one shared space, give each key to the closest node ID, route to it in about log-n hops, replicate for safety, and keep healing through constant churn. Thanks for watching. Next time a swarm of strangers finds exactly who holds a file with no server in charge, remember the trick: keys and nodes share one number space and closeness decides everything. Follow how it all runs for more. See you in the next one.